Yeah, hi. Thank you for inviting me. So I am Sujith Mangalathu. So right now I am working as a research scientist for Equifax Atlanta. So here I mainly work on graph analysis for fraud transactions. So I did my PhD at Georgia Tech in 2007. After that, I spent a couple of years as a postdoc in UCLA, California. So my background is mostly on structural engineering and statistics. So my degree was civil engineering with emphasis on statistics. So my master's is on statistics. Okay. So here is my presentation outline. There is a slight shift from the announcement. So I will go with a smart city and what are its features and enablers. So what are the challenges to smart cities risk assessment program? So how can we use a data-driven approach to solve some of the issues with smart cities? So I focus on two kind of infrastructure system. One is bridges and the other is buildings. So this is specifically applicable to California because most of my research was on California, or research was on infrastructure systems in California. And I will give a brief outline of what are the future directions or conclusions I noted from the I noted from the study. Basically, I took around 7 years for the infrastructure assessment of California. So these are some of the conclusions from that 7-year work. 7 year is not my PhD program. So my PhD is only 4 years, and then remaining 3 years my postdoc and my stay in Equifax. Yeah, so the key features of a smart city is it should be energy efficient. Uh, if you have any questions, free to ask at any time because yeah, I don't mind that. So the key features of a smart system are energy efficient. So it should have a real-time monitoring because based on monitoring, they decide whether they should use more energy or less energy. It should be connected. For example, we have a transportation system, pipeline system, a telecommunication system. There should be a connected system between these various infrastructure systems. It should be of data-driven nature than a manual effort. And even for any disaster, it should get back to its functionality very early. The system should be so resilient. So nowadays, cities are trying to be smart. And if we look at the global smart city market, the projection is very high. By 2025, we have around more than $2,500 billion will be spending on the smart city effort. So what are the fundamental enablers for building smart cities? So we have a large amount of data coming from various sources these days. So this can be from the historical data or doing some live experiment or from the sensors we placed on the infrastructure systems or from the social media. And we need an effective communication system. And once the data is transferred to a computational platform such as cloud or other servers, we have to do some big data analysis and visualization to have some informed decision on the state of the infrastructure system. The key thing is the data and the computation, and my presentation will be focused only on these two. So what are the challenges associated with the data? Because as I said before, we have a large amount of data for the infrastructure systems. Mostly they are coming from the sensors we placed on bridges or buildings, or from the historical effort or historical records. There was a lot of earthquakes in California, and we have the detailed record of the damage of various structures during that earthquake. Similarly, we have a damage of the infrastructure systems during hurricane. Nowadays, a new data source is emerging, that is social media, because people like to post everything on social media, and a new data source. It can be either text or visual description. Also, a lot of research centers and labs are doing experimental studies. So that is another source of information And we can even use image and video from drone footage or any other sources. So if we rely on traditional computation analysis, it might not be sufficient to tackle the problem. For example, if we want to analyze the city of California, how the city responds to a disaster, one thing, we don't have enough computational power to analyze such a big scale analysis. It's computationally expensive and it's very difficult to achieve convergence. Also, we don't have much data. We have some data, but that may not be enough to have a validation for a city scale analysis. Also, transportation, if we look at the connected systems, the transportation network is connected to the power system is connected to the water system. So there is a lot of interdependencies between systems in a smart city. So the new or the current approach to solve this problem is a data-driven computation technique. So we can enhance the use of machine learning and artificial intelligence to solve this kind of problems. So we can have an informed decisions from the big data or machine learning analysis. So as I said before, my background is mostly on civil engineering, and I will give you how machine learning is used in civil engineering in the context of natural disasters. So the Google is using artificial intelligence to predict floods in India and one use case. So such a decisions help the emergency teams to make informed decisions. So there is a lot of uncertainty associated with earthquake. So we never know when it will happen or how strong it will be. But right now we are, based on our historical data, we are using deep learning to predict is there any aftershock associated with an earthquake. Also, we are using machine learning for various aspects of the earthquake. So here I am going to present what is my contribution to the infrastructure analytics for smart cities. So currently, the California Department of Transportation is having an earthquake assessment system. So basically, they are using my model for the risk assessment of bridges. So that's what I am going to explain in the initial part of my presentation. So in the second part of my presentation, I explain how can we use machine learning to predict the damage of buildings. So I briefly touch the network analysis in my presentation. Okay, so coming to the challenges of smart cities infrastructure risk assessment. So here the risk means in the context of disaster. The disaster can be earthquake, hurricane, or tornado, or any other natural or man-made disaster. So the risk here has a different meaning compared to a network risk or any other things. So here risk is in the context of natural disaster. So here the smart city risk assessment should be, so the challenges in smart cities risk assessment is we should have a sustainable and resilient structure. Even if there is a disaster, we should get back to our functionality without much delay. Any delay in functionality will affect the lives of many people. For example, if a city or if a residential area is damaged, so we have to move the people out of the residential area. Now, we cannot keep them for long at some places. So we have to take them back as soon as possible. So our system should be resilient such that we have a quick monitoring of the various residential areas, and we should mark which are the buildings that are ready to occupy, or which area is safe, or which area needs more retrofitting. So given the uncertainties in the risk-informed decisions, we have a great challenge. How can we address this situation? So I explain how can we use a data-driven approach for the risk assessment of bridges. So here I am going to the motivation of my PhD research. We have some earthquakes in California. If we look at the historical earthquakes, there are three major earthquakes in California. One is at 1971 San Fernando, the other one is at 89 Loma, Prieta, and the recent big one is of Northridge at 1994. So here I am showing some of the pictures of the structures damaged during that earthquake. So one of the critical things is, after a disaster, the emergency team should move from one area to other area without any disruption. But if we have damaged structures like this, it affects the emergency response team's mobility. In other words, if there is a residential area and is disconnected because there is a collapse on the bridge, so we cannot move the people away from that area very easily. So if you look at the economic losses, for 89 Loma earthquake, the economic loss is between $6 to $10 billion. So around 100 bridges damaged during that earthquake. For 1994 Northridge, the situation was much worse because we have more than 240 damaged bridges and the economic loss is between 20 to 40 billion US dollars. So these are some of the failures of bridges noted in that earthquake. So the question often comes is, how can we improve the resilience of transportation networks? Or what is an efficient way we can do the post-earthquake emergency response? Because we cannot make all our structures earthquake-proof. Some structures are likely to collapse. So if there is an alternate way the emergency team can go, so we can practically mitigate such effects. So which bridges should be critical, which bridges should be of earthquake-proof, and what are the viable alternate ways connecting one residential area to the emergency area or other parts of the state. So currently there is an earthquake assessment program with the California Department of Transportation, or CALTRANS. So there they have a ShakeCast system. The ShakeCast consists of two things. One is shake map and other is bridge fragility. So if there is an earthquake in California, the shake map produces a map such that what is the intensity of earthquake at the various locations. So once this map is there, we know where are the bridges located. So if we have the fragility curve of the bridges, so we can combine this intensity with fragility. For example, here on x-axis, it is intensity measure and y-axis is the probability of damage. For example, if the intensity is 0.5, we can say that the probability of collapse for that bridge is only 24%. But there is an extensive damage, the probability of extensive damage to the bridge is more than 42%. Or there is highly likely that the bridge has some slight damage during that earthquake. So basically, we can use the earthquake map and a curve like this to assess the state of the bridge. So here I am giving an example. Here, my x-axis is the intensity measure. You can simply consider this as the intensity measure of the earthquake, and the y-axis is the probability of failure. So if we know the intensity measure at a location after an earthquake, and if we have curve like this for every structure in California, we can quickly assess what is the state of damage, whether it is in a slight damage, or whether it is in a moderate damage, or whether it is in a complete damage. If the probability is close to 1, we can say for sure that it is in a high damage state. For example, an intensity of measure of 1, the probability that there is some damage on the bridge is more than 90, or some moderate damage on the bridge is more than 50%. So we can get a quantifiable measure what is the likely state of a structure after an earthquake. But the computation of that curve is not so easy. One thing is, we are generating this curve through a lot of numerical analysis. To generate some curve like this for one structure will take at least 1 day. So if the challenges, what are the challenges associated with generating that such type of curve? So we have more than 24,000 bridges in California. Excuse me. Each bridge has its own properties. They vary in age, they vary in location. The number of spans means how much the span stands from one edge to the middle of the column. This is a 2-span bridge. This is a 3-span bridge because there are 2 columns and 3 spans in between. So we have different frame system. The bridges can be on 1 column or 2 column or 3 column. And we have different cross section. Here I am considering the column cross section. It can be here, it's a rectangle. Here it is a circle. So it can be hexagon. It depending upon the structure which we designed at that time. So how can we generate fragility curve for 24,000 bridges? So the one way, assume that we have only one set of curve for each bridge. Here I have fragility curve means this is the curve which I refer to as fragility curve. So other extreme is we assume that each bridge has different set of fragility curve and to generate 24,000 bridges. As I said before, it will take at least 1 day with the available computation power to generate the fragility curve. So this is generating 24,000 bridge curve is not practically possible. So there are various studies that do this. How can we reduce the number of bridges? So basically, I am producing the groups based on ANOVA. So I compare the performance of bridges during earthquake. So if 2 bridges have similar performance during an earthquake, I group them. And if they have a different performance during an earthquake, I group them differently. So I use some statistical study to see whether the bridges can be grouped together or not. So this is the numerical model which I explained before. So here we have detailed finite element model for each component, and we do the finite element analysis for different possible earthquakes in California. So based on that only, we generate the fragility curve. So based on my statistical analysis, I came up with the 129 bridge class. So here I have the information of the bridges in California, the 24,000 bridges. So I did some random sampling and I did some analysis to come up with a 129 bridge class. So what I am saying here is, if we generate curve for the 129 bridge class, we can essentially have a proper earthquake management system for bridges in California. So here I am invoking the use of machine learning techniques. So I will give a brief touch on what is the different machine learning technique. Especially the California team want to know what are the important parameters, because they are going to impose or implement this model in their system. So they didn't allow us to go to advanced machine learning model because they have a estimate why the damage is varying with each bridge parameter. So I only went with linear, ridge, lasso, and elastic net. So basically, if you have the data, what we are trying to get is a just right model. So this is a underfit model and this is an overfit model. So basically, we can get a just right model by finding the coefficients of the regression. So in machine learning, we always divide the data into training and testing set. So we establish the prediction model based on the training set, and we evaluate the performance based on the testing set. So here in this study, I consider 80% of my data as training and the remaining 20% as testing. So based on some comparison, I came up with a suggestion that Lasso regression is the best one for this type of bridge model. It has the lowest mean square error and the lowest absolute error. So it also helps me to identify what are the important parameters for the bridge. The important parameter, of course, is the intensity of the ground motion, but other parameters, what is the type of soil, what is the configuration of the column, or what is the mass, whether there is any live load on the bridge. So that kind of factors are very important in identifying the damage of the bridge. So this is some intensity measure chart. So here in bridge, we have different components such as column, foundation, abutments. The abutments stands for the one at the end of the bridge. So here we can identify which parameter is important for each component of the bridge. For example, most of the components are affected by the ground motion intensity, but how long the bridge is, the span length or how long the bridge is also a significant parameter, and it's affected by the various factors of the bridge. So I suggested a methodology for the fragility curve analysis. So in a nutshell, the method goes like this. So I generate some data from numerical analysis. So I connect the input and the damage with some lasso regression. So once I have a model, I generate large number of demand value. Then I know the capacity of the bridge, and I compare the demand with the capacity to generate the curve. So basically, the curve looks like this. So this is the fragility curve which I explained before. So here on x-axis, I have the intensity measure, and on y-axis, I have the damage state. So contrary to the previous, I generate this type of curve for each component in the bridge. For example, column or abutment or foundation for bearing. So if an earthquake comes, they can simply look into the curve and see what is the damage for the component, what is the damage for the column, or what is the expected damage for the abutment, or what is the damage for the bridge. For example, 8.5 intensity measure creates a damage more than 75% for this bridge. So this is a very old bridge in California, and that is kind of expected. So how this is used in California Department of Transportation. So I suggested a methodology to generate fragility curve, and then we ran lot of analysis to generate fragility curve for the 129 bridges. So with the 129 fragility curve, we essentially are covering more than 90% of the bridges in California. Once we generate the fragility curve, they implemented that fragility curve in an earthquake alerting system. So right after an earthquake, they generate, for example, if there is an earthquake happens in California, they produce the intensity map at various locations. Once they have the intensity map, they look into the fragility curve and they have different inspection alert. So if the damage is more than 60%, they put the bridge in 6th red category. Or if the damage is between 40 to 60, they put the bridge in orange category. Or if there is less than 20% of the damage, they put the bridge in green category. So we ran the model for a fictitious earthquake. So here I am showing that it can give the color tags. For example, for this earthquake, this bridge is in a red damage state. The other components are in an orange damage state. Red means that bridge should be close to the public and no one is allowed to travel till it is repaired or restored. If it is an orange bridge, it means that the emergency team can go through that bridge without much trouble, but it shouldn't be open to public. The green means it's safe and the public can go through that bridge without any question. So for a fictitious earthquake in California, we ran this model, and based on the model, we suggest that okay, these 119 bridges are of high inspection priority and should be closed. So the other bridges are of medium priority and only emergency team should be allowed. So look into this scenario. If there is an earthquake in California, within seconds, we can identify which bridges are in red state, which bridges are in orange state. So the emergency team can take the orange bridges to transport the people, or the transportation department can directly go to the high bridges or high damage state bridges and do their inspections and restoration work. So it can save considerable amount of time and effort and help the emergency team and the transportation team to have some informed decisions. So right now, what they do is, if there is an earthquake, they do some random evaluation. So they send some people to bridges and see whether it is good or bad. And based on their inspection, they decide whether to open that bridge or not. But with this type of curve, there is no manual inspection. Oh no, there is still need for manual inspection, but there is less manual inspection. So basically, we can send the people to the bridges which we mark as red. So that is the advantage of this method. So though CALTRANS or California Department of Transportation doesn't want to use advanced machine learning model, I also suggested another machine learning model for the damage assessment, but it's mostly for an academic purpose, not for a practical implementation. So this is my work on bridges. So now I am switching to buildings, and I will give an example. How can we quickly estimate the damage of buildings after an earthquake? So I used the Nepal earthquake as a case study. So for the Nepal earthquake that happened in August 2014, the PGA, or the intensity of the ground motion, is not that high, it's only 0.61 G. But if we look at the damage, more than 3,400 buildings damaged in that earthquake. So if we look at the economic loss, it's between 500 million to 1 million US dollar. So here I am suggesting 3 different approaches to estimate the damage. So one thing, if we know the earthquake and if we know the building characteristics, we can estimate the damage. Or if we have the social media information, that's another source of information which we can use to estimate the damage. Or other option is if we have the image of the damage structure. So let me go with the earthquake and building characteristics first. So after an earthquake, we know what is the intensity of the ground motion. So how far the building, okay, this is the most slide. So after an earthquake, we know what is the epicenter or where the earthquake happens. So we know how far this building from the epicenter. So here VS30 and SA stands for the intensity measure at this place. So once we know the age, because the old buildings are more susceptible to earthquake because they didn't follow the advanced construction practices. So then we have the number of stories. So if we know these parameters, we can build a machine learning model to see or to predict the damage of the building right after an earthquake. So here I am putting into 3 categories. So one is ready to occupy, that is a green bridge, so the people doesn't have to be evacuated from that building. So if there is a red category, that building is unsafe. So the people has to be evacuated very fastly from that building. So there is another category, yellow. It means that we are in a confused state whether it is unsafe to occupy. So some engineer has to inspect that building and make a decision whether it should be marked as green or whether it should be marked as red. So if we look at the decision boundary, it's very complicated because we don't get a good decision boundary based on these parameters. So, but still, our model, we tried various machine learning model. So basically, our model estimated an accuracy of 64%. So it's not that great, but currently we don't have any methodology to predict the damage of a building. But this method can at least fairly identify what are the buildings that are likely to be in green. So if we can predict the yellow buildings more correctly, so that's also another advantage which we can get because we can allot the resources or we can allot the engineers to that yellow category building. So the bridges that are unsafe to occupy, this model didn't predict that correctly. So we tried whether we can do some other methods to predict the red category buildings. So I am going to go with the damage descriptions. So now, okay, let it come. Now we are living in a social media time. So we have a large amount of information in the Twitter or Facebook or other sources as post. So basically, we can get some information from this post, whether whether that area is safe or whether that area is damaged or what is the extent of damage in these areas. For example, if we can see some words like a minor crack, home safe, or some keywords like this, we can easily categorize that building to green. Or we say that something like collapse or detached beam, so we can easily put that in red. Or something like chimney, there is shifting of foundation, but there is no mention regarding safe or unsafe. We can put that buildings in yellow category. So based on Nepal earthquake, we collected various tweets and other social media posts, and we classify the building based on the keywords that appear in their post. For example, if we mention the foundation or collapse, that building is in red category. Or if we say minor cracks or structure good, minor, so we put them in green category. And the chimney structure is damaged, we put them in yellow category. So this is the model. So from the data, we divided it into training set and test set. We did a natural language processing NLP model on the training set and did the performance evaluation on the test set. So here the model is fairly better compared to the earlier model. So we are getting a accuracy of 86%, but be careful here because this is solely based on the social media information. Sometimes people might not even post, or they might not be in a state to post something on the social media. So trusting this model blindly is an issue because we don't know whether people will tweet or not, and what are the keywords they use in their tweets. So the other information is, if we have the damage structure, if we have the image of the damage structure, can we use that to predict the earthquake? For example, here in the left side, I am showing 3 different states of the building. So this is the red state building because the building is collapsed. The yellow state means there is some damage, but an engineer has to inspect whether it should be ready to use or not. Here we have only minor cracks, so we can see whether it's safe. So the residents shouldn't be evacuated immediately. So based on some image analysis, we can do the feature abstraction, and we can classify this into 3 areas. The red means unsafe to occupy, yellow means ready to occupy, no, yellow means inspection, and green means ready to occupy. And when I know data comes, we can easily classify whether this is a red category or yellow category. So we have a large amount of damage structure images. So basically I use that to build a machine learning model and test that on Nepal earthquake. So here also, we don't have much accuracy compared to the Twitter-based information. Here the accuracy is only 62%, but we can get some good amount of information from this image-based classification. Contrary to the traditional image classification, this image classification is very tough because each building is different. They don't have a unique pattern. And yeah, there are a lot of complications associated with the images collected during the earthquakes. Also, another drawback is the building construction practices in California might be totally different from other parts of the country or other parts of the world. So coming up with a global machine learning model is also a challenging task here. So here we have to rely on some regional machine learning models. So here is my conclusion. So one thing is that we are relying more and more, or we are using more and more machine learning for the damage assessment. Because of the computation complexity, that big data analysis or machine learning provides a way to tackle these challenges. So during my work, I suggested a machine learning model for the risk assessment of bridges. So currently, the California Department of Transportation is using that system to predict the damage of bridges after an earthquake. So I also suggested some methodology for the damage prediction of building. So the advantage of these techniques is right after an earthquake, we can predict the damage of each various buildings in California. So here I use the social media information and image analysis. So this is the end of my presentation. Thank you for your time, and if you have any questions, I am ready to answer. So if you need any additional information, you can see in my Google site. Yeah, thank you. I will wait for questions. Hello?
Hi, I wrote my question in the chat.
Oh, okay. How to see that? Okay.
I can just tell you, I was wondering, how do you tie the social media post to the specific building that it's referencing?
Okay. Sorry, can you say that question again?
How do you tie the social media post to the building that it's talking about?
Okay. So what we did is we collected a lot of social media posts earlier, and we extracted the geographical coordinates of that post, and we have the actual state of that building from the inspection reports. So based on that, we trained the model.
So,
for example, if you teach from a Berkeley campus, we can extract your geographical information and we can see what are the structures surrounding you. So, and based on further inspection report, we identified whether that building was in green, yellow, or red. So then we build a machine learning model.
So I guess the assumption is that the social media post is being made at the location.
Yes.
Okay.
Yeah. So that's a good question. That's our fundamental assumption.
I had a question about the bridge model. Since the model has been deployed and is being used in California, have you reevaluated its accuracy and have you made any adjustments to it, like since it was deployed, or changed it?
No, the question is we have to wait for some actual earthquake to see the real evaluation, because we don't know if the earthquake comes in the way that we expected. But the counter answer that I can give is this is based on the best available model we have, because this model is well validated with the experimental results, and we compared that with the Nepal earthquake. But Nepal earthquake is not a high intensity earthquake, but for Nepal earthquake, our model was able to get a 80% accuracy. But we should be careful while extrapolating that to high intensity earthquakes. But for low intensity earthquakes, yeah, the model works perfectly fine. But we have to wait for some additional data. But I should not say, okay, earthquake should happen so that I can get the data. Yeah, that's kind of contracting. But yeah, so we have to get more data to test the real accuracy. But right now, we can say, my expectation is it would predict. Yeah. Yeah, I think, yeah. Hello?
Yeah, thank you.
Okay, thank you. Then I am stop sharing my presentation. Yeah, thank you all for your time.
Thank you for the presentation.
Yes, thank you.
Thank you, Sujith. That was awesome.